Hi everyone. Okay, so in these notes we are going to see a new method, the power series method. If you remember what we saw last week, we saw the characteristic equation method, and that was useful to find solutions of homogeneous linear ODEs with constant coefficients. So that was an important assumption that we have, an important condition that we have to check. The coefficients of the equation have to be constant. Okay, but what happens if we have an ODE where the coefficients are not constant? What can we do in that case? Well, in some cases we can apply this power series method. So before talking about the method, let's talk a little bit about power series. So what is a power series? It's a series of this form where we have, like here, the power m. This a is called the center of the series. And okay, it's like this sum where we have infinite terms. So and these am are all constant numbers, and x is, as usual, the variable. Okay, so this is a power series. Remember, we have a series, as you can see, the center of the series, and of course in each term we have a power, and these are the constants next to each power. Okay, so what is this element, mathematically speaking? Let's say we can see this element as a limit of what we call partial sums. Partial sums, maybe is obvious from just the name, is summing only a few terms. The first terms, let's say, we start with 0, with m equals 0. So I only have a0 and x minus a to the power 0, which is 1. So the first partial sum is here. Then we can sum the first two terms, which would be a0 plus a1 x minus a. Then we can compute the next one. We sum until m equal 2, and so on and so on. So for each m, capital M, we have this expression where we add all the powers 0, 1, 2 until m, capital M. So these are called the partial sums of the series. So this power series is just the limit of m when goes to infinity of these partial sums. Okay, since this is a limit, this limit can take any value. Well, maybe not any, but at some point, maybe for some coefficients and some x and some center a, this expression can take the value infinity. So we would like to detect for which points x this expression is finite. That would be our first goal. And that has a name. We say that the power series converges at x0 if the series is finite there. So what we mean is just that this limit is a real number. Okay. So what I just said, given a power series, we would like to know which are the points such that the power series converges at those points. We can put a name to this series. Let's call it F. And a family of examples for this type of power series, for the power series itself, are these Taylor series representation. I don't know if you remember, but given a function smooth enough and a point A, we can compute, depending on how differentiated is the function g, we can compute the Taylor series representation, which is given by this expression, g in A, then the first derivative divided by 1 factorial, and so on and so on. So these coefficients for the Taylor series representation are unique determined by the function g. And this is a huge family of examples for this type of series, the power series family. Okay, so this is a very general example because I can choose any g that I can smooth enough such that it has a power series, a Taylor series representation. Okay, then maybe a more explicit example. We have here this one. Just all the coefficients here are equal to 1, and then I only have the powers. 1 plus x squared, and so on and so on. So we can see this as a Taylor series representation also of this function g, centered at a equal to 0, or we can also do this computation by hand, which is, I think, nice, so we are going to see it. We take the partial sums, remember, for sum m is just considering the first m terms of the series, and then we multiply this expression by x, another line, and then if we distribute here the x, we have this expression. We kind of lose this 1, and then we have x is instead, once we multiply by x squared, this x, once we multiply by x, is an x squared, and so on and so on. So the last one would be m, the power would be m plus 1. Then if we subtract these two lines, this one minus this one, what we get is, in this side of the identity, everything will kill itself, let's say, apart from 1 and x m plus 1. But on the other side, we have this expression, and in common, these two terms have in common the sum, the partial sum, so we can rewrite this in this way. And finally, if this x is not 1, then this amount is not 0, so we can divide by that number. And that's what we do here in the last step. Okay, so now we have the expression for the partial sums. And now, remember that this series is the limit of its partial sums. And having the expression of the partial sums is quite useful when we want to take the limit, because now here we know that this is finite if and only if x is the module of x is strictly less than 1. Okay, so I think this is a nice example that can be seen as a Taylor series representation, but also we have this, let's say, by hand calculation that is also good to know. Okay. And if you remember, when we were talking about power series, we are interested in these points, the points that makes this series finite. So here we found that all the points for this particular example that makes this series finite are the ones that have modulus less than 1. Okay, later we will give some names to these, like we have a radius of convergence, or and this will be called the interval of convergence, but okay, maybe we talk about it later. And now we are going to see some basic properties of the power series. Okay. First of all, the easiest one, the power series always converges at its center, A. It's quite simple to see because if we choose x equal to A, this is exactly 0. So that's the easiest property. Then, here are the names that I was talking about. Okay, so imagine that there are more points, not only the center where the series converges. Then we call that interval the interval of convergence, and usually has this form. Are the point x that its distance to A is less restricted than r, and r will be called the radius of convergence. Okay, so if this number happens to be finite and positive, of course, then the picture that we get is this one that we have here. We will have this interval of convergence. We have the center A and these extremes of the interval. And we will know that inside this interval, the series converges. And outside the interval, the series diverges. That's what we will know. And maybe you are wondering what happens. So what happened when x is exactly this point here, right? This point here or this point here. Okay, we will see some examples, but so far just we have this picture. Okay, so if the series converges only at its center, then this radius is exactly 0. There are no more points, just the center. And then if the series converges for every x in R, then the radius of convergence is infinity. So we will have these 3 cases each time we are working with power series. Okay. So how can we find this radius of convergence or the interval of convergence of a series? We will have mainly these 2 tools, and in each exercise we can choose one of them. The 2 tools are the ratio test and the root test. What do they say? So we denote this limit as C, and we have 2 conclusions and then one part that we don't know what to do. If this limit is less than 1, strictly speaking, then we will know that the series converges. If it's greater than 1, we will know that the series diverges. But when C is exactly 1, we have no idea, which means it's not that we have no idea, it's that this test doesn't help, it's inconclusive. And same for the root test. We have this limit, and if we call this quantity C, we have exactly the same consequences. If this C is strictly less than 1, then the series converges, and then if it's greater than 1, then the series diverges. And when it's equal to 1, we have no idea, which means that the test doesn't help. Okay, let's see some examples. So we can use these two tools and see how to use them and how to conclude and how to find the radius of convergence and the interval of convergence. Okay, so first example. This is a power series. We have a series, we have powers, we have these numbers, the coefficients. So we are in the setting, and the center is 0. Okay, so if we look at the test, we need, oh, here maybe I have to correct it. Ah, no, it's okay. Okay, so we have to choose this CM in both cases. So we will take the whole expression here, not only the numbers, also with the variable x, and call that CM. For instance, here we're using the radio test, so we have to calculate this quotient, and okay, we replace just the information. Here we have to put m plus 1 for the first part of the limit, and just m for the second part of the limit. After some calculations and arrangement here, you can see that some numbers go away, and some variables also. Then this limit goes to 1 when m is going to infinity. So finally, this limit is x squared over 4. And once we have the limit that in general depends on x, can depend on x, we go to the test and say, okay, then if that limit is less than 1, we know the series converges. And if it's greater than 1, we know the series diverges. So going back to the example, we just split this result of the limit in those cases. So if this is strictly less than 1, we can conclude that the series is finite. Okay, now we see the interval here. If we solve this inequality, is exactly this. So with this information, we already know the radius of convergence is 2. Okay, then if this is greater than 1, then the series diverges. Then, okay, solving this inequality, what we get is this other interval. So it's exactly the picture that we were describing at the beginning, where the radius of convergence is a finite number, r. So here r is equal to 2, 0 is the center, and we know that inside this interval the series is finite, outside is infinity. Okay, but as I was asking when we introduced the concepts of radius and interval of convergence, what can we say here in these extreme points? Can we say something? Okay, so remember that the test doesn't help in those cases, so we have to do something else. The something else is working with the series by hand. What do I mean with that? Just take the series, replace the values of the extreme of the interval, and see if you can say something about the convergence. So, for instance, here, let's choose one. Let's replace the series at x equal to 2. So here we have the series, the 2 instead of the x, and now 2 to the power 2m is exactly this, is 4m. So finally, what we get is this other series. And what happened with this series? When we remember that this series is the limit of its partial sums. So we can say, okay, I have no idea if this series converges or it doesn't, but I can take a look at its partial sums to have an idea of what's going on. So we try to see what happened with the partial sums of this new expression. Okay, the first one is -1. It's just 1 times -1 to the power 1, so it's -1. The second one is -1 plus 2, which gives this 1. And we can calculate it, the third one, the fourth one, the fifth one, sixth one, and so on and so on. And we will get to this blue line, let's say. And we can see that the values are increasing, and depending of if the m is even or odd, we are kind of going to -infinity or infinity, right? If we choose these terms, we can imagine that we are increasing. We are taking the values 1, 2, 3, 4 until infinity, let's say. And now if we look at the other part, -1, -2, -3, so on, we can imagine that we are going to -infinity. So that idea can be formalized, and you can write expression of these partial sums where we consider this 2m as the final term of the sum, and then we go to infinity. And then, well, as an exercise, you can find the expression of this partial sum, and you will get this expression, and you can see this -infinity that we were talking about. So we can conclude that our power series diverges at these 2 points, the extremes of the interval. So finally, we can claim that the interval of convergence is -2, 2, and the -2 and the 2 are not included in this interval. So now the picture is this one. We can close the picture. The series converges here in the open interval -2, 2, and diverges outside, including these 2 extremes, -2 and 2. Okay. So, remember what happened in this example. We have our power series. We choose one of the tests, radio test or root test. Those tests will give information with open intervals, but we won't know what happened in the extreme of the intervals. Like here, in this example, the extremes of the interval are -2 and 2. And then what we can do to decide what happened in those extremes is just see by hand if we can calculate, if we can compute the partial sums, and see if we can compute by hand, just with the limit of the partial sums, what happened with this series at those points. So fortunately, in this example, we could solve because the partial sums are easy to get, and in the exercise that you will have to do will be the same. Okay. Second example, we have this power series, we have the powers, we have the series, we have a center. So here the center is -2. And here let's choose the root test. So again, we call C the whole expression, not only the numbers, let's say the coefficient AM, the whole expression, we call CM. And then by the root test, we have to calculate this limit, which is the same of this. So because these power is killed by this root here. And this limit is equal to 0 for every x in R. And we know that 0 is strictly less than 1. So this root test says that the series converges for every x in R. So we are in the case where the radius of convergence is infinity and the interval of convergence is the whole R. Okay, this was maybe easier than the first one. And third and last example of this part is this other series. We have this expression, which is m times m minus 1, m minus 2, until 2 times 1, so all the numbers. The product of all the numbers less or equal than m. We have the power, we have the series, we have numbers here, we have the center. So here the center is a equal to 3. For instance, we can use the radio test again. Remember that we call the whole expression Cm. Cm doesn't matter, it could be Bm, any letter, but we have to take the whole expression, the whole term. Then when we want to apply the radio test, we have to be careful because we are dividing by this expression, so we have to ask that this x is not exactly 3. Then we just add this assumption here and compute this limit. Well, some things are cancelled and so on. So what we get is this expression. Modulus of x minus 3 times this limit, which is trivially infinity. But we have this infinity for every x not different from 3. So, who is 3? Remember that 3 is the center of the series, and we already know that every power series converges at its center. So 3 for sure is a point where the series converges, but for any other number different from 3, this limit is greater than 1 because it's infinity. So the test says that the series diverges for every point different from 3. So we are in the case where the radius of convergence is 0 and the interval of convergence is only 3, which is the center of the power series. So, summarizing. The goal of this lecture is to learn how to use power series to solve ODEs. So far in this first part, what we saw is what is a power series, and the power series have a radius of convergence and an interval of convergence, and we saw two tools to calculate these two things. The two tools were these two tests, the radio test and the root test. Remember, we know what happens when these limits are strictly greater than 1 or strictly less than 1, and when it's exactly 1, we don't know and we have to check by hand what happened. Okay, so as usual, if you have any questions, then you can contact me. And so far, this is the first part of the second lecture, where we also have 3 examples with these 3 different situations, where the radio of convergence is finite, where the radio of convergence is infinity, and where the series converges for every x in R.